everybody. Welcome to today's session of the Spectral Geometry in the Clouds seminar. Today we have the pleasure of having Paolo Luzzini from École, who will talk to us about the spectral asymptotics for the buckling problem. So Paolo, the floor is yours.
Thank you very much. Thank you very much for the introduction and for this kind of hospitality in your seminar. So as Jean said, today we talk on the spectral asymptotics for the buckling problem. And let me mention from the beginning that is mostly based on a joint work with Davide Buoso from the University of Eastern Piedmont, Luigi Provenzano from La Sapienza University of Rome, and Joachim Stubbe from the PFL of Lausanne. And like directly introduce the statement of the buckling problem. So for a domain of finite measure, the buckling eigenvalue problem reads in this way, as you can see on this slide. So on the left-hand side of the eigenvalue equation, one has the Laplacian operator, while on the right-hand side, the standard Laplacian. And the condition that we consider are the Dirichlet boundary conditions. So maybe a first difference that one can notice between this problem and more classical eigenvalue problems is that on both sides of the eigenvalue equation, one has an operator, while usually, of course, one has the identity on the right. So for this reason, this falls in a wider class of problems, which is called the eigenvalue problems for operator pencils. But still, this is a well-investigated problem for which is known that the spectrum is made of positive eigenvalues of finite multiplicity, which can be arranged in a divergent sequence in this way, as you can see here. And from the physical point of view, from the physical meaning of the problem, it is of relevance in the theory of mechanics of deformable solids, and is derived from the so-called Kirchhoff-Loff model of plates. In particular, the buckling problem is related with the critical buckling tension that leads to the deformation of a clamped plate. And so just for curiosity, in order to explain a little bit better the physical meaning of the problem, I think that it's better to read the first few lines of the Wikipedia page about the buckling, which says that in structural engineering, buckling is the sudden change in shape of a structural component under load, such as the bowing of a column under compression or the wrinkling of a plate under shear. If a structure is subjected to a gradually increased load, when the load reaches a critical level, a member may suddenly change shape and the structure and component is said to have buckled. So here in these two images, you can see two examples of buckled structures. Here on the right, you can see a concrete column which has buckled under the compression of too much weight. And instead, here on the left, you can see an example which is more related to buckling of plates, since a plate is nothing else than a thin structure. And you can see an airplane where on its metal skin, on the metal surface, it presents these wrinklings, these waves that you can see mostly on this part due to the light. And these are produced by the buckling of the skin. And as I've read on this aviation forum, this is quite common effect to see on surfaces of plane, but luckily this does not compromise in any way the stability and the safety of the plane during the flight. So this was just for curiosity. We are not really interested in physical application of the buckling problem, but we are interested into looking some mathematical questions, and in particular into studying the asymptotic distributions of eigenvalues. And let me briefly outline the remaining part of my talk. I will start with some well-known results on the more classical case of the Dirichlet Laplacian. For sure, most of you know very well this type of result, but maybe I think that it's better to recall some of them in order to introduce some notation and also to make some observation that will be useful in the second part of the talk. Then I will focus on our work on the buckling problem, and I will focus on some aspects. First of all, I will consider some Weyl-Sharp estimates that we prove on the eigenvalues, or at least on some quantities related to eigenvalues. Then, as a consequence of these Weyl-Sharp estimates, we will derive a new proof of the already known Weyl law for buckling problem and the minimal assumption on the domain. After the first term in the expansion, that is the Weyl law, we will consider two-term asymptotics, and we will compute the second term for some very specific domains. And finally, something which is not directly related to asymptotic of eigenvalues, but which somehow arose when we were considering the buckling problem in one dimension, and it is an extension of an inequality which was due to pain, and in the case of one dimension for the buckling problem. And as I've said, this part of the buckling problem is based on joint work with Davide Buoso, Luigi Provenzano, and Joachim Stubbe, and is contained in this preprint here that is currently submitted for publication, and that can be found already on the archive. And let me briefly mention that in the first draft of this preprint, we were assuming a regularity condition on the domain, which actually immediately after we realized that it was not needed. So in this talk, I will present the result, dropping this regularity assumption on the domain. So as I've said, let's recall some results for the Dirichlet Laplacian. As all of you know very well, this is the statement of the eigenvalue problem for the Dirichlet Laplacian, with this sequence of eigenvalues diverging to plus infinity. And maybe one of the first and for sure most famous result about asymptotics of eigenvalues is due to Hermann Weyl at the beginning of the 20th century, which proved that the asymptotic behavior, the first term of the asymptotic expansion of the Dirichlet Laplacian eigenvalues, has this disorder, and the constant is this one. And as it is well known, asymptotic behavior for the eigenvalues can be rephrased also in terms of another quantity, which is the counting function. And I recall that the counting function is nothing else than the function which counts the number of eigenvalues below a real number z, as its name says. And so the Weyl law for the counting function can be equivalently restated in this way. So this for what concern the first term, and of course, once one has understood the first term, it is of interest to compute lower order terms. And there are many results in this direction. Let me mention this famous result due to Ivry, which proved somehow this conjecture on the second term, which was already formulated by Weyl, which proved that under some regularity assumption on the domain, that is under smoothness assumption and the Billiard condition, the counting function for the Dirichlet Laplacian has this two-term expansion with this order, and the constant of the second term is this one. There are, of course, many other results. For example, we have seen in a seminar of these talks a result presented by Simon Larsson for a result in collaboration with Rupert Frank, which showed that it is possible to prove a two-term expansion dropping the Billiard condition and assuming only Lipschitz regularity for the domain, but not for the counting function, but for a more regular quantity that is the first Ritz mean that we will see later. Its precise definition. And so another point of view in order to understand the asymptotic behavior of the eigenvalues is to prove explicit bounds. And this direction, Polya conjectured that the eigenvalues, or equivalently the counting function, can be lower bounded or upper bounded by their Weyl term. And he proved its own conjecture for the Italian domains, that is domains which can cover the space through the pairwise disjoints congruent copies of the same domain. And this somehow has been extended, but in full generality, it remains an open conjecture, but somehow a step toward the understanding of these bounds has been done later by the so-called Berezin-Liyau inequality, which somehow can be understood as an average version of the Pauli inequality. Indeed, it says that the average of the first eigenvalues, which is this quantity here, which somehow is more regular than the single eigenvalue, can be lower bounded by this term here, which in view of the Weyl law, it's asymptotically sharp. So as for the eigenvalues, one can rephrase things for the counting function. Also for this more regular quantity, one can rephrase things in another framework, which is the framework of Riesz means. And I recall that the Riesz mean of order gamma, it's the function defined by this sum here, which is always a finite sum since the eigenvalues are diverging to plus infinity and we are taking the positive parts. And also it is possible to show that it can be also represented as a suitable integral of the counting function. And by Legendre transform, one easily seen that bounds for the eigenvalue averages are equivalent to reverse bounds for the first Riesz mean, and in particular the Berezin-Liao bound reads in this way for the first Riesz mean. And another step in order to understand these quantities here could be the one of seeing whether if it is possible to reverse the Berezin-Liao bound with the first term, which is the same Berezin-Liao term, that is the first term which is sharp, and adding some lower order correction terms. This has been done, for example, in this work by R.L. Provenzano Stubbe, which proved that under some regularity condition on the domain, it is possible to reverse the Berezin-Liao bound. That is, for example, prove an upper bound for the eigenvalue averages with the first term, which is sharp, that is, which is the same term as in the Berezin-Liao inequality, but adding a second term, which is of the correct order under some regularity assumption of the domain. And so they proved a series of results of this type, and in particular, they also proved that bounds of this type can be obtained also without requiring any regularity assumption on the domain, but in this case, one gets only the first term, a sharp first term, and a second term for which we cannot estimate its velocity. So these are only, of course, some results for the Dirichlet Laplacian, and this doesn't want to be in any sense a review of this matter, but only some results which I think are interesting in the point of view of this presentation. And let me finish this first part about the Laplacian with a very, very simple observation. And so, as we have seen, it is possible to prove an upper bound of this form for the first Riesz mean, which is the Berezin-Liao bound. And we also seen that it's possible to reverse the Berezin-Liao bound, providing a lower bound with the first term, which is sharp, and with some lower order correction term. So these two-sided bounds immediately implies a Weyl law for the first Riesz mean. So immediately these two bounds imply this asymptotic behavior of the first term of the first Riesz mean, which in turn, by applying some simple Tauberian theorem, one can go down from a Weyl law for the first Riesz mean to a Weyl law for the counting function of the eigenvalues. So this is only a simple observation to see that these two-sided bounds in the framework of Riesz means can be also understood as a simple way to prove Weyl laws. So this completes this part on the Dirichlet Laplacian. So we can go further and return to the Backlund problem, which I recall that the definition of the Backlund problem, which is this one. And of course, actually, we are not considering its classical formulation, which is this one, but we're considering its weak formulation in H20, which is this one. And so, as we have said, this problem admits a discrete spectrum, which is made of positive eigenvalues of finite multiplicity, which diverges to plus infinity. We are represented in this series, counting together with their multiplicities, and which also can be variationally characterized through the min-max principle in this way. And so we are interested in in their asymptotic behavior as j tends to plus infinity. And so we will formulate things in terms of counting function and also for its mean. So I recall that the counting function for the Buckling eigenvalues is this one. And it's already known that the Weyl law for the Buckling counting function is this one. That is the Buckling problem admits the same Weyl law as the Dirichlet or Neumann Laplacian. And this is not, of course, is not a surprise. And this is because usually the first term does not depend on boundary conditions. And since the Buckling problem in the eigenvalue equation of the Buckling problem, the two sides of the equation differs by only Laplacian, one expects that the asymptotic behavior of the counting function will be the same one of the Dirichlet or of the Neumann Laplacian. So this result has been obtained earlier by several authors. So here I mentioned Rosenblum, Kozlov, Liu for the derivation in Riemannian manifolds, and also it appeared very recently a note by Friedlander, which proved with an approximation argument, quite simple approximation argument, this Weyl law. And so our aim is first to provide lower and upper bounds for Ritz means, which are Weyl sharp, and as a corollary, as an application of the result, we will derive a new proof, a new and simple proof of this Weyl law for the Buckling counting function. So we start with the lower bounds for eigenvalue averages, or upper bound for the first Ritz mean. And we note that Levin and Protter in the 85 said that for a domain of finite measure, the Berezin-Liyau inequality of this form holds for the Buckling eigenvalues, or for the average of the first k Buckling eigenvalues, or for the first Ritz mean. However, once we went through the proof of the result of Levin and Protter, we noticed that there was a gap, and actually by their proof it follows a weaker inequality, that is an inequality with a bigger constant, which is not Weyl sharp for the average of the first k eigenvalues, or with a smaller constant for the first Ritz mean. And also we were not aware of anywhere in the literature where this gap was mentioned or solved. So we decided to, as a first goal, to revise the proof of Levin and Protter and provide a corrected proof, staying in the same spirit of their proof. And so let's see a brief sketch of the proof of the Berezin-Liyau inequality for the Buckling problem, and see where the gap of the proof of Levin and Protter is, and how can this be solved. And so we take uj to be a system of eigenfunctions with this normalization condition on gradients, and of course by Fourier transforming the normalization condition and by Fourier transforming the eigenvalue equation, one has these two relations here. So for any r greater than 0, one can rewrite the sum of the first k eigenvalues in this way, and simply by using this true equality here. And this can be lower bounded in this way, since outside the ball of radius r, the integrand is always positive. So in order to provide a lower bound for this quantity here, we need to provide a lower bound for this integrand, and then optimize this quantity with respect to r. So Levin and Protter in their proof proceeded in this way. So they consider the modulus of p squared times the first k Fourier transform eigenfunctions. So they consider this quantity here, and they rewrite this quantity in this way by incorporating the modulus of p squared inside the Fourier transform by considering the gradients of the generalized eigenfunctions. So by integration by parts, of course, one gets this. And since the gradients of the generalized eigenfunction are an orthonormal system in L2 by the normalization condition, by the Bessel inequality, one recovers this upper bound here. So they recover this upper bound here, where, as you can see, there's this d term here appearing in front of this inequality, which comes from the fact that we are summing d terms here. So by plugging in this bound in the previous inequality, one recovers this lower bound, which depends on R, of course. And by optimizing this lower bound with respect to R, one obtain this, say, Berezin-Liao type bound, but which is, of course, not by sharp, since it appears this term here, which is d to the power minus 2 over d, which is always strictly less than 1. And so by this argument, one does not recover the claimed sharp Berezin-Liao inequality, which is this one. And so we somehow fix this gap, remaining in the same spirit of their proof. So to fix this gap, one has to consider this quantity here, that is p modulus of p to the power 4, and incorporate this term here inside the Fourier transform by considering the Laplacian of the generalized eigenfunctions. So again, by integration by parts, one can recover here this equality here. And since in this case the gradients of the generalized eigenfunctions are a complete system with respect to in the gradients of function in H10, one can use the Parseval identity and recover this upper bound. And so as you can see, in this upper bound does not appear the d term. And so by plugging in this upper bound in the previous lower bound, in this one, it is possible to recover the claim and the claimed Weyl-sharp Berezin-Liao inequality. So this was only to provide a revised proof of the Berezin-Liao inequality. And so the next step in our work was to try to provide some reversed inequalities for this quantity here, or for the first Riesz mean, with some sharp first term and with lower order terms. And a first simple result that we can, so we want to find some form of reversed Berezin-Liao inequality, and the tool that we want to exploit is the so-called average variational principle, which is due to RL and Stubbe. And somehow the idea inside this variational principle can be traced back to the work of Kröger on upper bounds for the Neumann-Laplacian. So this abstract principle says that if we have a self-adjoint operator H in some Hilbert space with a discrete spectrum, and we denote by Q the quadratic form with its quadratic form domain. So if we take a family of functions Fp in the quadratic form domain, which are indexed by P, which varies in some measure space M, and also one takes a subset of this measure space, which we call M0, then one has this inequality here for the first Riesz mean. And this can somehow be interpreted as an average version of the classical variational principle for the first Riesz mean, or for the equivalently for the sum of the first k eigenvalues. And this has turned out to be an effective tool to provide reversed Weyl-sharp bounds for a series of problems. For example, for the Dirichlet Laplacian, the work that I already mentioned by RL, Provenzano, and Stubbe, or also for the Dirichlet B Laplacian. For example, there's a work by Boso, Provenzano, and Stubbe. So in our idea, we wanted to apply also this result to this abstract tool to the buckling problem. And however, this somehow turned to be a little bit more tricky. This is because the buckling problem, as we have said, is an operator pencil. And so for this reason, the Hilbert space in this case is not L2, but it's H10. So here the scalar product is not the the L2 scalar product, but it's the L2 scalar product of gradients. And this complicates quite much the choice of an effective family of vectors to be chosen in order to apply the variational principle. However, we somehow managed to apply this principle to obtain some results. The first result that I want to present you, it's the following. So by almost directly applying the variational principle, it's possible to recover that this lower bound for the second Riesz mean holds in a term of a length, where one has the correct order and also the correct constant. So let's see how this proof goes. So we apply, as we have said, the average variational principle, which I recall the formulation, which is this one, where we use the functional setting of the buckling problem, which is this one, with buckling eigenvalues and buckling eigenfunctions. And as a family of functions, Fp, in this case, we decided to take the uj to be the eigenfunctions of the Dirichlet Laplacian operator, which correspond to a Dirichlet Laplacian eigenvalue capital lambda j. And the measure space is, of course, n with the counting measure. And as M0, we take a subset of M, which is made of a finite subset of indexes, which we will clarify later who is. So by plugging in all these choices in the average variational principle, one can recover an inequality of this form here, where one does not have exactly the first Riesz mean, because also there is this eigenvalue multiplying it. However, it is possible to rewrite this quantity as a difference between the first and the second Riesz mean, and also rewrite the right-hand side in this way, simply by adding and subtracting z squared. So at this point, we want to be able to deal with this right-hand side. So we want that Riesz mean of known problem appear in this right-hand side. So in order to this to happen, we make a choice for the subset of indexes in the variational principle, and we take those indexes for which the Laplacian eigenvalues stays below z squared. So if we choose this set of indexes to be put here, we can substitute this sum with the full sum and putting the positive parts. And of course, we can estimate the second term since it's negative with the full sum and the positive parts. And also we write the right-hand side by means of a derivative in this way. And so we end up with this differential inequality for the second Riesz mean. And so we deal with this first term by using some reverse bound for the buckling, for the Laplacian eigenvalues, which were proved by Boso, Provenzano, and Stubbe. And we deal with this first term by using the Beresin-Ligliau inequality for the first Riesz mean of the Dirichlet Laplacian. So we can deal with these two terms, and so we can integrate this differential inequality and proceeding with some limiting argument and derive this lower bound for the second Riesz mean. So this was a simple application of the average variational principle. And the second step, we wanted to derive some finer estimates and obtaining also some lower order terms. And so in order to obtain this, we applied the variational principle with another choices of function of vectors Fp to be put in the variational principle. So we apply the variational principle with the Fp to be the generalized eigenfunction of the Laplacian, cutted off by a suitable cutoff, which is in H20 and which is also bounded. So with this choice in the variational principle, one can prove that we were able to prove that this lower bound for this quantity here holds for all this cutoff. So it's a lower bound which depends on L2 norm of the cutoff, of its gradients, and of its Laplacian. So by this bound, we wanted to recover something which is more informative and does not depend on the cutoff. And so the idea here is to take the cutoff that approximate the indicator function of the domain omega. And so we constructed an explicit form of this cutoff function for which we were able also to estimate their norm, the norm of the gradients and the norm of the Laplacian in a tubular neighborhood of the domain. And so with these choices, we were able to obtain a lower bound for this quantity with a Weyl-Sharp first term and with some lower order term which we can not control in the case we assume no regularity assumption on the domain omega. Also, by assuming some regularity on the domain, for example, if you assume Lipschitz regularity on the domain, by this general lower bound, we can recover a lower bound, which of course has again a Weyl-Sharp first term and a second term of the expected correct order, say, which is 3/2 plus d/2. And also, this can be used to recover some bounds with the control on the second term, but with weaker regularity on the domain. That is, we can assume this type of assumption on the regularity of the domain. That is, for omega which is less than 1, we assume that the supremum limit of the measure of the tubular neighborhood of size h of the boundary of omega over h to the power gamma is finite, which is somehow related to the Minkowski dimension of the boundary of omega. And under this assumption, we can recover a lower bound, which of course has again a first term which is Weyl-Sharp and a second term of this order here, that is 2 minus gamma over 2 plus d/2. So this our Séminaire result regarding bounds with also estimation of lower order terms. And as I've said, this type of bounds can be used also to recover a simple and self-contained proof of the Weyl law for the buckling problem. So for a domain of finite measure, this bounds immediately implies the Weyl law for the second Riesz mean. And this Weyl law for the second Riesz mean in turn is equivalent to the Weyl law for the counting function. So the proof it's the same as we have seen for the Dirichlet Laplacian, for the simple observation I've made at the beginning of the talk. So since R2 is nothing else than 2 times the integral of the first Riesz mean, so by integrating the Beresin-Liao bound of Levin and Protter, one can get a upper bound for the second Riesz mean. And also by the lower bound we have proved for the second Riesz mean, we immediately obtain the Weyl law for R2. And so again, by simply noting that R1 is the integral of the counting function and R2 is the integral of the first Riesz mean, then we apply twice a simple Tauberian theorem of this form that you can see here and recover from a Weyl law for R2, a Weyl law for R1, and applying another time the same Tauberian theorem, one gets the Weyl law for the counting function from the Weyl law for R1. So this somehow it's a simple application of these bounds that we have proved, and which imply this new proof for the Weyl law. So this somehow concludes the first part of our work regarding bounds and the Weyl law, and then we turn to consider 2-term asymptotics. So if omega is sufficiently smooth, one could hope to apply the argument which are nicely exposed in the book of Safarov and Vasiliev and recover a 2-term asymptotic expansion for the buckling counting function of this form here. So one expects that a 2-term expansion of this form holds for the buckling counting function, where the constant of the first term is this one, where A is the principal symbol of the Laplacian. And one can immediately realize that it's exactly the Weyl constant. And instead, C1, the constant of the second term, it's this one, where without entering into details, this shift function here is a function which is related to an auxiliary one-dimensional problem, which is related to the buckling problem. However, the result of the book of Sakharov and Vasilyev are applies to elliptic operators, and or at least are stated for elliptic operators and not for eigenvalue problems for operator pencils. And to us, or at least I can speak for me, it's not clear whether they can be rigorously extended to operator pencils, since honestly, I'm not really an expert on this technique of microlocal analysis. So we were not able to show that this is rigorous, but at least we can formally apply their argument and try to compute this shift function here, and in turn to compute this C1 constant of the second term. So by formally applying their argument, we are led to state the following conjecture. So we believe that for a bounded domain with smooth boundary, the two-term expansion of the buckling counting function is this one. So as you can see in the second term, in the constant of the second term, there are two parts, and the first part, this one with the 1,4, is exactly the constant of the second term of the Dirichlet-Laplacian eigenvalues, while for the buckling also has this second term in the second part in the second term. So this for what concerns the buckling counting function, and of course, if we believe that this holds, by integrating this two-term formula, we also believe that the formula for the first Riesz mean has to be this one. So as I said, we were not we haven't confirmed this conjecture in generality, but we will show two examples for which we can see that this is somehow a good guess. So we will compute the second term in the case that omega is a ball, and in this case we will show the conjecture for the counting function and for bounded intervals in R. And in this case, we will show this second form of the conjecture for the first Riesz mean. And this is because usually low-dimensional problems has not a sufficiently regular counting function to have a second term. And this can be seen, for example, for the Dirichlet-Laplacian on a bounded interval, which of course has only a first term, not a second term. And let me mention that we are very, very recently informed that the case of ball have been already treated in a very long paper by Auschbau, Getzesi, Mitrea, and Teschel in the 2010, where they consider the perturbed Krein Laplacian, and which in turn they show that it's spectrally equivalent to the buckling problem. So let's see, however, how the proof goes for balls and for bounded interval. So let's start for the case of balls in RD. So it's of course suffices to consider the unit ball centered in zero by translation invariance and by rescaling. And so by passing spherical coordinates, it's well known that the eigenvalues of the Dirichlet-Laplacian corresponding to angular momentum L are the solution of this equation here, where J is the standard Bessel function of the first kind. And similarly, one can do the same for the buckling problem and obtain that the eigenvalues are the zeros of this equation. So as you can see, it's the same up to a shift in the order of the Bessel function. However, in both cases, the multiplicity of an eigenvalue corresponding to angular momentum L is given by this constant here. And so since one has to consider zeros of Bessel functions, we denote by x with this subscript the nth zero of this Bessel function. And it's known the asymptotic distribution of this zero of the nth zero of the Bessel function. And for example, it can be found in the Abramowitz and Stegan, and it's this one, the asymptotic behavior in N. So a little bit of notation. We will use we will denote by sigma DLN the nth eigenvalue, the nth buckling eigenvalue corresponding to angular momentum L. We will do the same for the Dirichlet Laplacian. And of course, one has this relation here between buckling Laplacian eigenvalues and zeros of Bessel function. We also denote, we also introduce counting functions related to, associated to eigenvalues with angular momentum L. So one has this relation, and of course, the full counting function is nothing else than the sum between overall angular momentum of the counting function with angular momentum L times the corresponding multiplicity. And so the two-term expansion for the Dirichlet Laplacian, it's known, and it's this one. So this, in the case of a ball, it's exactly this one. The second term is this one. And so in the case of ball, we can restate the two-term expansion in this form. So for a ball in RD, we prove that the difference between the buckling counting function and the Dirichlet counting function has this leading term with this constant. So let's see how the proof goes in dimension 2. So the proof in dimension 2, it's quite simple, since in this case the multiplicities are constant whenever L is greater or equal than 1 and always equal to. So this is the claimed second term, which, as we pointed out, it can be restated in this way. And so the proof is nothing more than rewriting the buckling counting function as a Dirichlet counting function by shifting the index of the angular momentum and to recover this equality here. And by this equality immediately implies this asymptotic behavior, since each of this term provides a contribution of 1 over pi square root of z. And this is because by the known asymptotic distribution of zeros of Bessel functions. So this is the quite simple proof in dimension 2. The proof in dimension 3, it's a little bit more involved, but follow the same strategy. And so we want to prove that this holds. Exactly this is the two-term expansion. And by arguing in a similar way, that is by rewriting the buckling counting function as the Dirichlet counting function and shifting the index of the angular momentum, and also using this known summation formula for the multiplicities of the eigenvalues, one can recover an equality of this form. And so to obtain the claimed two-term expansion, one needs to show that this sum here is exactly a little O of this order. And this can be done in 3 steps by seeing whenever this sum stops, to also estimate the multiplicities, and by also estimate the difference between these two counting functions. And we have done these 3 steps. First, by showing that this sum stop at an L max, which can be bounded by the square root of z. Also, it is seen by the explicit formulas for the multiplicities that they can be upper bounded by L to the power d minus 3. And finally, the difference between these two counting functions can be estimated that it's never bigger than 1. And this is because the zeros of Bessel function, which have an index which differ at most by 1, that is these two Bessel function, are interlaced. That is, their zeros are interlaced, and so immediately one recovers that the distance between these two counting functions is always less or equal than 1. So this is the proof in dimension for balls in dimension d greater or equal than 3. And so we also consider the case of bounded intervals. For bounded intervals, the buckling problem, I recall that the statement, it's this one. And what we prove, as I've said, it's a two-term expansion for the first Riesz mean. As I've said, low-dimensional problem could not have a sufficiently regular counting function to have a second term also. And the proof in this case, in the one-dimensional case, it's to do as explicit computation, as much explicit computation as we could. And so in this case, it's possible to show that the buckling eigenvalues can be written in this way, where the sequence Tj is nothing else than 0 when j is odd, and it's the first 0 of this equation here whenever j is even. So by this representation of buckling eigenvalues, and by computing the asymptotic behavior of the zeros of this equation here, and then the asymptotic behavior of this sequence Tj, it's possible to recover the two-term expansion for the first Riesz mean in case of a one-dimensional problem. So this concludes the part on asymptotic estimates, on what we can say about the asymptotic behavior of buckling eigenvalues. But while we were considering this problem here in one dimension, somehow naturally we consider another problem in one dimension, and that is the problem of extending an inequality by Payne. So Payne in the 55 proved that for a domain of finite measure, this relation between the first eigenvalue of the Dirichlet B Laplacian and the first eigenvalue of the Dirichlet Laplacian and the first buckling eigenvalue holds. That is, this relation here holds. It is possible to prove this relation by the variational principle for all these eigenvalues. And again, by using the variational principle, it is possible to extend this inequality in this way for all j. However, one can maybe ask if this inequality here holds also for other eigenvalues than the first. It's somehow natural to ask this type of question, since it holds for the first, when one wants to see whether it could be true also for other eigenvalues. And since we have done some explicit computation for the one-dimensional case, and since in a previous paper by Boso, Provenzano, and Stubbe, they have already done some explicit computation for the eigenvalues of the Dirichlet B Laplacian in one dimension. So we were able to show that this inequality here for the first eigenvalue holds for all eigenvalues j when we are in dimension 1. So we extended this inequality for all eigenvalues, but only in dimension 1. So let me briefly finish with some observation and maybe some future perspective starting from this work. So we believe that some of these techniques, some of these results can be extended to more general operator pencil problem of this form, for more general operator pencils. As we believe that it could be really interesting to see whether the two-term expansion can be proved in more generality than for some specific examples. For example, trying to adapt the procedure explained in the book of Safarov and Vasiliev and prove a two-term expansion for the counting function, or also try to generalize the work by Franke and Larsson and see whether it's possible to prove a two-term expansion for the first Riesz mean for the buckling problem. And also it could be interesting to see whether this inequality here holds maybe in other domains than for problems in higher dimensions. And as maybe some future research, I note that the asymptotic behavior and bounds of this problem here, that is the Dirichlet problem for the fractional Laplacian, where by u equals 0, I mean the meaningful Dirichlet boundary condition for this non-local operator, that is for the fractional Laplacian. Asymptotic behavior and bounds for this type of problem were studied, for example, by Laptev and Geisinger. And also there's a nice review by Frank regarding this problem here. So maybe it could be interesting also to investigate the fractional Backlund problem, that is this type of problem here, where we are considering two different fractional power of the Laplacian. And so this concludes what I wanted to tell you, and I thank you very much for your patience during my talk.
Thank you very much for the talk. So I will clap for everyone. And we have time now for questions. So if you have questions or comments, please just unmute yourself or write in the chat if you don't feel like speaking. Now is the time. Okay, so I wanted to ask you something. You almost answered it in the last slide, but for the last inequality that you showed by plane in higher dimensions, have you started thinking about the strategy or even looking at examples?
Well, we tried something, but we weren't able to arrive at anything. We started to think about, but nothing meaningful at this point came to us. Say.
Anyone else wants to ask something to Paolo?
So for the fractional buckling problem, do you have any idea on what relationship between S and T would be? I mean, I can't believe that this would work for any
I think that it will behave so as the difference. Well, one expects that it will behave as the fractional problem with an index which is the difference between these two, with these two powers. So the natural thing to expect is this one. But well, I've made some literature search, and I haven't seen anywhere stated this problem. So maybe it could be that it's not interesting enough. It's more interesting the problems for the fractional Laplacian, but maybe it could be something that one can look if there's some difficulty that arises in considering this type of problem. So well, we haven't really started to work on this problem, but maybe it's a nice thing to investigate.
Thank you. Anyone else wants to comment or ask a question? So if not, let's thank Paolo again. Thank you very much.
Hi everyone.
Oh yeah, go ahead.
Does we need some regularity about omega? The last problem.
For which problem? Sorry, for this one.
Yes.
Well, I don't know. I believe that at some point, well, of course, it depends of what one does want to obtain, but to obtain also estimate for lower order terms, of course, one needs at least some regularity on the domain. And to prove at least the divide law, I believe that is work without any regularity assumption on the domain. So I believe that it depends on which kind of result you are interested in proving. But yes, I believe yes. For need some regularity.
There is in chat a answer by who says that for S greater than 1, you will need more conditions on the boundary. So it's
yeah. Oh, yeah. This was stated for S between 0 and 1, and yes, also this case for S between 0 and 1, and yeah. Yes, of course. By this I mean the natural boundary condition for the Dirichlet boundary condition for the pro. Also, it's interesting to to investigate the higher order fractional Laplacian, but of course one needs the meaningful Dirichlet boundary condition for it.
Thank you very much for this talk and for being here for everyone else. We will reconvene next week, so June 28th, for a talk by Ari Laptev, who will speak about spectral inequalities for Jacobi matrices following Hundertmark and Simon. Thank you very much, and everyone have a great week. Bye-bye.
Thank you to everybody.
Bye-bye. Thank you.
Thank you. Bye-bye.
Thanks, Paolo.
Bye-bye. Thanks for the hospitality.